Good morning, everyone. My name is Aryan Karmare from Team Slayers. Our given problem statement is the space theme, and before understanding what exactly are we doing and how we are solving the problem, I thought I'll give you all a little bit analogy. So imagine you are in a self-driving car, and the weather is inclement, the weather is not pleasant, and it is certainly not at all suitable for driving. Now, the car suddenly pulls to the side because the sensors cannot capture enough data. The same thing happens in space when you have to dock two satellites, but the solar weather is heavily unpredictable with a lot of storms, making the sensors difficult to capture the data and actually dock the satellites. So here we, Team Slayers, introduce Symbiosis. Symbiosis is a multi-agent framework that uses hyperdimensional cognition, centralized pose estimation, and Pearson safety guarantees into a unified real-time operations environment. Let us understand this by adding an image of a spacecraft. So over here, I have added an image of a spacecraft, and immediately the Jensen gain is calculated. The Jensen gain measures how much sunlight is present on the spacecraft. A higher Jensen gain indicates it is difficult to dock. We even check whether this image is valid, and we even check if this image is a debris or not via OOD error. Moving on, these are the graphs formed by this image, and we check the system overview and telemetry. As the Jensen gain is very low, this means the image is clearly visible and it is very easy and suitable to dock right now. So the current action is telling us to dock. We also measure various possibilities to ensure that we are not taking a wrong step. This is done by HDC or hyperdimensional cognition. In hyperdimensional cognition, around 10,000 vectors of phase, position, all of these dimensions are captured into a singular vector. This singular vector it gives you an informed decision, which is the recommended action, which is to proceed slowly with this much confidence score. And this confidence score is from these four components, with pose being the highest and anomaly being the lowest. After this, after getting all of our metrics, we compare it with NASA's suite dataset. So NASA had given a couple of parameters that these parameters are supposed to be, essential for practical flight. So we get our parameters and we compare it with theirs. And this shows that we pass all of NASA's technical claims and the pipeline moves on. Moving on, we also have an autonomy consensus matrix, which is multi-agent with perception, cognition, and action. So all of this pipeline is SHA 256 verified and validated and audited as well. Now, in case of a spacecraft emergency, we can simulate various challenges, let us say perception challenge or thermal anomaly, and then we can find out what that effect plays on the Jensen gain. So as you can see over here, the Jensen gain dramatically changes, the range dramatically changes based on the conditions. Now let us understand something interesting. What happens when a system cannot dock? Because docking is one thing, what happens in the other case? So, after uploading a very bright sunlight image, after uploading this image, we see the Jensen gain is 45 degrees, which is completely unsuitable for it to dock. So these are the graphs, and even the system overview is telling us to hold position because the visibility is pretty less. Moving on, even the HDC, after running 10,000 times, tells us to hold position mainly due to the uncertainty. And all of the NASA suit tests are passed, and hold position is the correct decision over here. But I want to dock, and docking is essential for me. So I would figure out various pathways on which I can dock. This is done through the Armstrong protocol. So currently the Jensen gain is 45 degrees. Let us understand why. what are the reasons why docking is infeasible over here? So mainly, docking is infeasible due to six reasons. Either the sunlight is too much on the image, or the satellite is drifting far away, or the satellite is overspeeding, or the satellite has a lot of OOD error, or it can be a system failure, or many times it can be all of them combined into one. So all of these six cases are mentioned over here. Based on the image, you get an automatic recommendation with a predicted Jensen gain value suitable enough to dock. And after I choose my recommendation, so this is the sunlight recommendation, this is the keeping hold recommendation. After I choose my recommendation, I can again change it. I can see the trajectory. I can see the predicted Jensen gain. I can see the collision bound and everything. And after I confirm the parameter, the docking has successfully happened as the Jensen gain has reduced, so we can proceed slowly to dock, and the pre-commit validation like the trajectory clearance, the crew gets notified, and even the SHA 256 is audited. Now let us understand how exactly is the worst possible scenario calculated for our docking. This is done by a method known as Klopper-Pearson. Monte Carlo simulations calculate everything. They do not calculate the worst, they take out the average. So we use Klopper-Pearson, which takes the worst case scenario from the observed rate. This is the formula. So now let us understand how exactly the safety guarantees and confidence scores are turned into guarantees using the conformal calibration. The model is trained on 3,500 known test images. After training, we calculate the value of E hat, which gives us a distribution free guarantee. Now, the path which the satellites or the docking mechanism take is not straight. And this path is explained by CWH equations, which are shown over here. Push forward does not mean go forward. So, our spacecraft, what we assume is that push forward means to go forward. This is not really true because the path curls. So, these are the equations that describe the curl. The core USPs of this project are the transparency. There's no black box, everything is transparent. The logs are all tamper proof. All of this entire space mission is autonomous and it runs it on its own. The entire thing is self aware and it knows when it's guessing. Last but not the least, it is proven safety with certainty.